Chapter 8. In this unit, what we're going to do is we're going to solve systems of linear quadratic and quadratic-quadratic equations, both graphically and algebraically. And we're also going to look at solving both linear and quadratic inequalities with one or two variables. So the first thing that we'll do is we'll define what is a linear quadratic system. Well, if we remember what the definition of linear is, meaning a straight line, and quadratic, meaning our parabola, a linear quadratic system of equations is a system in which one of the equations is linear, so it has the form of y equals mx plus b, and the other one is quadratic, meaning it's ax squared plus bx plus c. What we are looking at when we go to solve these systems is we're determining what x and y values are the same in both graphs. So in calculus class, in order to determine the shaded area of the diagram between the parabola y equals x squared and the line y equals x plus 6, what we need to determine first of all is the points of intersection between the parabola and the straight line. So we're going to do this using our graphing calculator. So we're going to start off with getting our calculator, clearing it off. We want to adjust our window settings, and if we look at this, if we assume each tick mark is worth 1, we've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12. So my x settings go from a negative 8 to a positive 8, and my y settings go from, let's say, a negative 1 to a positive 12. And if I was to just graph that with no equation, I now see that my grid matches up. So now if I look at we're going to graph the straight line one first. Y equals x plus 6, and I'll explain why afterwards. And then underneath we're going to put the x squared. And then we press graph. And there's my replica of what I see on the page. So what I want to do is I want to determine these 2 points of intersection. So to do that with the calculator, it's second calc and it's choice number 5, intersect. Now, it'll tell you what graph you're on. I'm on the y1, I'm on the straight line 1. And it's easier to travel along a straight line graph than along the parabola. So I'm going to move closer to that first point of intersection, right here. Press enter 3 times until intersection comes up. And I get the point negative 2 and 4. So negative 2 and 4 is one coordinate of intersection. So what I want you to do is I want you to pause for a moment and determine what the other coordinate intersection point is. So the next point of intersection is 3 and 9. So the next part says, use the method of substitution or the method of elimination to algebraically determine these coordinates of intersection. So if you remember from last year when we were solving equations and we were solving them by elimination and by substitution, what I can do is I have that y equals x squared, and I have that y equals x plus 6. Well, if y equals an x squared and y equals an x plus 6, I can draw the conclusion that x squared has to be equal to x plus 6. That becomes my by substitution. So to solve this, bring everything over to one side, and then you're going to answer the question, what 2 numbers multiply to negative 6 and add to negative 1? The answer being negative 3 and positive 2. So my x values is that x can equal 3, right here, because if this equals 0, the whole thing would equal 0. And this one would be negative 2. So then what I can do is I can choose either equation. I don't have to do this for both, but I can choose either equation and I can solve for the y value. So if I used y equals x squared, y equals 3 squared, which is 9. There's my point of intersection. Or I could use the other equation, y equals negative 2 plus 6, which is 4. and 4. Part C says verify that the points in A and B satisfy the system's equation. So verify means check the answer. So I've got y equals x squared. Well, if I do a left and a right side, y equals x squared. If I use the point 3 and 9, y is equal to 9, x is equal to 3, 3 squared equals 9, it's verified. If I choose the other point, I've got negative 2 and 4. So on the y side I put 4, and on the x side I've got negative 2, which when I square it, gives me a positive 4. So this is verified. If I take my other equation, y equals x plus 6. So y on one side, x plus 6 on the other. Y is equal to 9, x is equal to 3. 3 plus 6 is 9. And finally, with the other point, y is equal to 4, x is equal to negative 2. Negative 2 plus 6 is 4. So to write the solution, I can write the solution as x can be equal to 3 and y is equal to 9, or x can be equal to negative 2 and y can be equal to 4, or I could write it as a series of ordered pairs. Either method would suffice. Okay. If we look at the note on the next page, in graphical mode, so when I'm trying to use, when I'm trying to graph these, I have to have my equation written in the form of y equals. When I'm using substitution, I need to have a y equals or an x equals equation in order to substitute one side in for the other. The graph of y equals x squared minus x minus 12 is shown. Algebraically determine the point of intersection of the line y equals 3x in this parabola. So y equals 3x, we can sketch this line without actually having to put this in our calculator. Remember, in y equals 3x, this is my y equals mx plus b. B is my y-intercept, and m is my slope. So in this equation, I have no y-intercept, which means the y-intercept is 0, and the slope is 3. So up 3 over 1, up 3 over 1, up 3 over 1. So then if I use a ruler, and it would be important that I used a ruler for this, so that I get this straight line. And what I'm looking for is I'm looking at where does this graph cross? Or where does this line cross the graph? So I want to make sure that I can see both intersection points on my graph. So I have an intersection point right here, and I have another intersection point right here. So if I was to write down what my points of intersection are, I've got a point here that's at negative 2 and negative 6. And I have another point that is at 6 and 18. Okay. If I decided to do this algebraically, what I could do is I could use substitution. Y equals this graph and y equals that graph. The two graphs would have to equal each other. So then I'd bring the 3x over, and it would become a negative 4. And then I'd solve what multiplies to negative 12 and adds to negative 4. The answer being negative 6 and positive 2. So I get x minus 6 and x plus 2. There's my 6. And then when I substitute it back in, if x equals 6, y is going to equal 18. And this one is x equals -2, which means y would equal -6. Okay, so I want you, let's look at the next question. I'm going to repeat this procedure for the line 3x minus 16. So in the equation 3x minus 16, 16 is my y-intercept. That's right here. And then I have my slope, up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, and so on, up 3 over 1. So if I graph this, what you may notice this time is that the graph actually only hits or looks like it's hitting the equation somewhere in here, which is a little bit harder to see, so solving this algebraically might not be a bad idea. So I get 3x minus 16 equals x squared minus x minus 12. So if I move the x over, I'm going to get a -4x. And if I move the -16 over, I'm going to get a +4. So two numbers that multiply to +4 and add to -4. -2 and -2, which means x would have to equal 2. And then when I substitute that into one of these two equations, y would then equal 3 times 2 minus 16, which would be -10, which looks to be this point right here on the graph. Okay. The final graph that you're asked to do is 3x minus 24. So in 3x minus 24, the y-intercept is at -24, and then my slope, up 3 over 1, up 3 over 1, up 3 over 1. So I use my ruler to join these points. And what do you notice? Oh, wrong button. I would hope what you notice is that the graph actually does not intersect the quadratic. So if we were to show that algebraically, what that looks like, I've got x squared minus x minus 6, right? Or sorry, x squared minus x minus 12 equals 3x minus 24. Bring the 3x over, it'll become -4x. Bring the 24 over, and I get a +12. So then I start to think. Can I think of two numbers that multiply to 12, a +12, and add to a -4? Nope, I can't think of any offhand. So if I can't think of any, then I go to the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac over 2a. So -b would be a negative of a -4, which becomes a +4, over b squared. -4 squared is 16, minus 4 times a times c, which would be 4 times 1 times 12, which would be -48, all over 2 times a, which would equal 2. So I get 4 plus or minus the square root of -32 over 2. Because I have a negative root, there is no solution. So let's use the results from these three graphs to draw some statements, some conclusions. If the equation, the linear equation and the quadratic equation intersect at 2 points, we can say that the graph of the linear quadratic system has two solutions, one at each intersection point. In the second example, where it only crossed the graph at one point, then the linear solution has one solution, or the system has one solution. And if there is no intersection between the linear and the quadratic equations, then the system has no solutions. In the process of solving a linear quadratic system, we end up solving another quadratic system. And if we use the quadratic formula for each of these, I could use that to help me determine it. And we're going to work backwards. Because when we work backwards, when the resulting quadratic equation, that was this equation right here, has no real roots, then the discriminant is what? The discriminant was negative, and I had no solutions. So if we go back to this equation right here, if we were to put that into the quadratic formula, negative b would be positive 4 plus or minus the square root of b squared, which would be 16, minus 4 times a, which is 1, times c, which is 4. So 4 times 1 times 4 is 16 all over 2a, or 2 times 1, which would be just 2. The discriminant in this case is equal to 0. So if the resulting quadratic has two real and equal roots, because when I did solve this, I got x equals 2 and x equals 2. So they were two roots, they were just the same root. The discriminant is equal to 0, and the solution, or the system, is one solution. Okay? And then the last one, which was the first one that we did, if I looked at the quadratic formula of this one, if I look more so just at the discriminant, that b squared minus 4ac, I get 16 minus 4 times 1 times negative 12. So that would be 4, or think of it as a negative 4 times 1 times negative 12 would be a positive 48. So then I would get the square root of 64. So my discriminant this time is positive. So if my discriminant is positive, then I will have two solutions. So if the resulting quadratic does not factor, then we use the quadratic formula. And in this case right here, because it only touched in one spot, we say that the line is tangent to the quadratic. Okay? So the questions that I would like you to work on, question number 1A, 2, 5, 7, and 8.